when we talk about atoms, when we look at them, we're going to use the familiar symbol that we see on the periodic table. And this familiar symbol that we have right here is that. And this center, C, is called the atomic symbol. So when you guys see a capital C, okay, you see a grade and you're like, oh no, I got a C. I'm saying, don't be so bad, you actually got carbon. Right? See right there, that's carbon. Okay? There are two other important parts of any elemental box diagram. Right? And down here I've got this one. That is the atomic mass. And it's in grams. Okay? And more importantly, it's not just in grams, it's in grams per mole. Okay? The final little bit that's way up here at the top, the 6, this thing is the atomic number. Right? The atomic number itself defines how many protons and electrons I've got inside of a system. Okay? So if the atomic number defines how many protons and electrons I've got, that means that I'm going to have 6 protons here and 6 electrons. Okay? And how am I going to find the number of neutrons? Well, neutrons weigh the same as protons. Okay? So a proton here weighs 1 AMU, it's atomic mass unit. Okay? A neutron is going to weigh the same. And electrons, if you look at them, the electron itself comes in, it's 1/1000th of an AMU. I should have looked that up before I started the video. But it's somewhere out there, okay? So it's a really small value. What that means is, for chemistry purposes, whenever we're calculating these weights, we tend to ignore electrons because you're going to need a lot of electrons in order to start influencing the mass of a molecule. So, and we're going to say that those are essentially no mass, because it's going to require so many electrons that we're going to need an atom the size with a molecular weight of 1,000 to really make an impact. And as we'll come to find out, those don't exist. So we're going to look at this and say, electrons don't have any mass, okay? All right. The things that only have mass, the things that we're concerned with, are protons and neutrons. So if I have something, let's round down, something that weighs 12, I take 12, I subtract 6, and the number of neutrons that I'm going to get out of this is going to be 6. Okay? So carbon has 6 protons, 6 neutrons, 6 electrons. It is the element of the beast. Okay? There you go. Okay. So what this means for us is that we have a standard or a neutral value for carbon, and we know what we can kind of expect when we have any carbon atoms. 6 protons, this defines carbon. All right? If I increase the number of protons to 7, it stops being a carbon and starts acting like a nitrogen. If I take one of those protons away, it now starts acting like boron. Okay? 6 protons defines what carbon is, and defines how carbon acts. Okay? The neutrons, what these guys do is the neutrons define stability. Okay? If I have carbon 14, and when I write it like this, that means that I've got something that's a mass of 14. Notice over here I had a mass of 12. This is a mass of 14, carbon 14. That means that I'm going to have 6 protons, because once I have carbon, that defines 6. The atomic number is always going to match what the elemental symbol is. 6 protons. It's neutral, so I'll have 6 electrons. And I'm going to have 14 minus 6, 8 neutrons. All right, now that I've got 8 neutrons, something special happens. The central atom, the nucleus of carbon, is now radioactive. And it slowly decays. And guess what? You've got carbon-14 in your body right now. We all have the same amount of carbon-14. So long as we're eating and we're breathing, we have this amount of carbon-14 that's in us. You ever heard of radio dating? It's because cosmic rays come down and they hit the atmosphere, carbon dioxide. Some of it gets turned into carbon-14. It gets absorbed by plants. Animals eat the plants. We eat the animals. And they're turned into a tasty hamburger. We eat the hamburgers. That gets into our bodies. So our body is continuously replenishing the amount of carbon-14 that's inside of our bodies. When we die, we get buried, we stop going through that process. So slowly the carbon that's inside of us, the carbon-14, it's got to do something because it's unstable. It starts going through radioactive decay. And in doing so, what ends up happening is that every 5,700 years, half of the sample of carbon-14 has decayed into decayed into nitrogen, excuse me. So we start losing that amount that's inside of us. What ends up happening is that we're able to date how old any kind of carbon-containing material is up to a certain range, because we have to detect it at a certain point. That's about 50,000 years off. So we can use carbon dating to figure out how old certain carbon materials are. Okay, and that's how old, because there's a certain amount of carbon-14 that's in all of us. All right. When I get to things that weigh a little bit more, like uranium-235, uranium-235 is radioactive. Okay? And because uranium-235 is radioactive, it's going to start shedding some weight as well. Okay? And it has to do not with the number of protons, but with the number of neutrons that's inside uranium-235. And when I talk about radioactive decay, you'll see more about that. All right? Well, let's take an example here. All right? And what I'll do is I'll fill in this table with some numbers, and I want you to tell me which element I'm talking about. So you want to get a periodic table so you can follow along with it. Just open up your book, look at the front cover. That's what I'm doing. Okay? And I'll put some information on here, and you tell me what we've got. So if I just put 5 electrons here, right? What element do I have? Assuming it's neutral. Okay? 5 electrons. Remember, atomic number is going to be the same as the electrons. So I'll put 5 protons there. Okay? So what do I have left? If I've got a 5, you know that that's boron. So I will write boron over here. Right? And the mass of boron normally is about 11, rounding up. So I'm going to put 6 neutrons there. Okay? Could I have used a different number of neutrons there? Yeah, I could have. Okay? Because all I gave you was the electrons. So you have a little bit of play there. Now some people are sitting there looking at this and saying, well, Dr. Rowe, what's going on with those electrons up there? I need to know what happens when we change the electrons. Change the electrons, it does not change what the element is. It doesn't change its stability. All it does is change its charge. Okay? Charge is defined by the electrons. Okay? If I have 7 electrons, my protons never change. So if I have 7 electrons, that means I've got a carbon with an extra electron. Electrons have a negative charge. Okay, so electrons have negative charges, protons have positive charges. To find out what the overall charge is, you match the two together, all right? So if I have something that's got 5 electrons and 6 protons, what's going to be the overall charge of that? We've got 5 negative charges, 6 positive charges. You're right, it'd be plus 1. And what element would this be? 6 protons, it's carbon. So this would be carbon plus. Okay, I usually put a circle around my charges there just to indicate that it's a charge, not an extraneous mark. Okay, let's do a couple more examples of this. All right. If I've got something that has 23 protons, okay, and supposedly it has a mass of 53, okay, which should tell me what element it is and tell me how many neutrons and electrons there are. So go ahead and hit pause, fill this out, and then we'll see if you're right. Okay, hopefully you came up with this. Protons, I said that there was no charge over here with my mass of 53. No charge, no big deal. That means my electrons have to be the same. Okay, so my charge is there. I look at 23 on the periodic table, and I know that my element is going to be vanadium, which is V. So V, 23. And what's going to be the overall mass of this thing? Well, I already know it's 53. So in this case, I've got vanadium, and this is 53. Okay? So that's what my element box is going to look like. And how many neutrons do I have? I've got 30 neutrons. Good, because I take 53, subtract 23, and that gives me the number of neutrons that I have. All right? So what about this? Suppose I give you rhodium 100. All right? Now I've given you the name of the element and the mass that's associated with it, rhodium 100. Tell me the protons, neutrons, and electrons that are in it. Again, hit pause. Good. All right. So rhodium, we looked this up in the periodic table. Rhodium comes in at 45. So the number of protons I've got is 45. The number of electrons that I've got is 45. Okay. The number of neutrons that I have, take 100, subtract 45, and I'm left with 55. Okay. Feel better about chemistry? I do. All right. One more example. Okay. And what I'm going to give you is, let's see, Br minus. Okay. Br minus up there. Now I want you to tell me number of protons, neutrons, and electrons there are. So look at we've got Br there. Remember the symbol defines the protons and vice versa. My protons are 35. Okay. The normal mass of bromine is 80. So I'll say that the mass of this thing is 80. So I'll write this as Br80 minus. Okay. There's a funny story about that. That doesn't exist. Haha, funny story. Can you even see that? Yeah. Br80, okay, with a minus charge. Right? 80 minus 35 is 55. No. It's 45. Don't assume I'm always right. So 35 and 45, that's my mass. Now what about the electrons? Okay. I've got a negative charge here, so that means I subtract a charge. 34 electrons? No! The minus charge means that I've got an extra electron. So for this bromine, what I've got are 35 protons, and I've got 36 electrons. Remember, electrons are negative, those are positive. 35 positive charge, 36 negative charges. I'm going to have one charge left over. So in this case, I've got 36 electrons. Okay? You should be able to do this for any sort of examination.